Okay. Okay. Yeah, let me go over this problem first, briefly. So that's problem number 30 in the textbook. You're not given the graph, okay? And you're given the description of the region. So we ask to find the volume. So basically, this will be triple integral of that shaded region in the three-dimensional space. So first, yeah, because it's inside sphere, right? It's below the cone, but inside the sphere above the XY plane. So we use spherical coordinates. In other words, we use transformation, and the given by x, y, z have three formulas there. So actually, what we did is that this rectangular box was sent to this shaded region, and then you change the triple integral to a triple integral over this box. Okay, then the box, clearly, rho is between 0 and 2. Theta is from 0 to 2 pi because it's around the whole circle. Yeah. Then phi, be careful. Phi is between pi over 4 and pi over 2 because the equator is when phi equals pi over 2. So use the spherical coordinates. Okay. Then you have the Jacobian. This part, this is a part coming from the dv. dv equals this derivative of the mapping times dv bar. Okay, so this is this is from the formula for the sphere coordinates. But actually, what we did here is we use a substitution for this triple integral. Then, because it's a box, E bar is a box, right? It's a pre-image of that region. So then you can quickly write down the iterative integral, then you find the answer, okay? And then evaluate each integral one by one, and finally you get 8 square root 2 pi divided by 3. But last time I also showed you two different ways to solve this problem. Suppose you do not want to use triple integrals, right? Spherical coordinates. How do you do this problem? Well, there are a couple ways to do. You can write the iterative integral, but first of all, double integral, then single integral, or the first one is single integral, double integral inside. So here, what we're doing is we're going to use double integral, then inside the single integral. How do you do that? Well, you have to project the whole region onto XY plane, which is the circle is radius 2, okay? But be careful when you project, there will be two parts there. The reason is, first of all, this is a disk, okay? The disk, and its integral over that disk was radius 2. The disk is in the two-dimensional XY plane. Then for each point in the disk, you have to find the range for the z. I know z is from 0, but what is the upper limit? The upper limit is a piecewise defined function because the top part is not the whole sphere, okay? And it's inside the cone and outside the cone. It's below the cone or just below the sphere, depends where you put it. You see, this is a picture. Let me show you, right? Could be here, right? Could be, could be here. If it's here, the highest point is determined by sphere. If it's here, right, it'll be inside, the highest point is determined by cone. So the range, the domain, the interval for the z variable for any fixed point in the domain D is determined by these two surfaces. So that's why you have to break into two parts. It's complicated, but it works. Break into two parts, and over over the circle disk inside the smaller disk, this is use z, the upper bound for z is going to be square of x squared plus y squared. But the over the yellow part, okay? And then you have to use a sphere. So the sphere, if we solve for z, the sphere z is going to be square root of 4 minus x squared plus minus y squared. So you have this two double integral we get. Then for each double integral, you have to use the polar coordinates to solve it. So I apply the using the polar coordinates for the first one and for the second one. The second one is a little bit tricky. The second one is I is between square root 2 and 2. The rest of them is the same. Okay, just you change the function to square root of 4 minus r squared. You know, changes this function to here, this function to here. Okay, so and then you evaluate it. Then I find out it's going to be pi square root 2 pi over 3. It's the same. Okay, exactly the same answer. Doesn't matter which way to go. Then the third method. There's 3 different ways to evaluate integral. So I'm going to use a vertical line. Begin with a vertical line first. Okay. So the triple integral become a iterative integral, but single integral outside, double integral inside. And how do we do that? Well, you look at the range, the domain for the z. I think the highest point for this one, yeah, the largest possible value for the z is going to be square root 2 because it's cut here, right? It's cut here. Okay, so z is between 0 and 2 for any z. You look at the cross section of the solid with this plane. Yeah, use a plane cut through the solid piece by piece. And so, but that solid, that cross section depends on the value of z, and actually you end up with a 2 discs. Okay, with the 2 discs, you have to take the larger disc and the inner disc, because the larger disc is determined by the sphere. The inner disc is determined by the cone. The radius is quite different. Okay, so but the radius should be expressed in terms of z. So the area, see, this part is just the area of the disc, but that changes depends on z. You'll get a function of z. Then it's going to be the difference of those 2 areas. Part of the areas with 2 discs. But you have to determine ZR and the little r. Capital R is determined by the largest sphere, and little r is determined by the cone, determined by sphere. So the difference here is the capital R here is going to be square root of 4 minus z squared, and little r is just equal to z because it's cone. Right? Then you take the difference squared. Take the difference, it's just 4 minus 2z squared. After you evaluate this single integral, you still get the same answer. Okay? But you see that it's a little more complicated, the second method, third method. A triple integral, there are 3 different ways to do. A triple integral can be evaluated using spherical coordinates or cylindrical coordinates if the region is nice. Okay? Otherwise, you can use a iterative integral in 2 different ways. Depends on the problem. Okay. In general, yeah, it will be. Yeah, let me begin with another page. Yeah. Then it's just a review. Okay. Yeah. So for a region in for a region in the 3-dimensional space, right? This is the E, right? How to evaluate the triple integral? Here's a function and the x, y, z, dv, right? There are a couple ways to do. One is you project the whole region into xy plane or xz plane. Really doesn't matter. Okay. Just for example, into xz plane, this is a shadow of the region. Okay. You project it. This is the d. Okay. You can project it to the xz plane. You can project the y plane. If we project to the xy plane, then this is the d. Okay. So you have to determine the d. Then this will be dA. Okay. And for each point x and y, you draw the line. You find the interval for the z. Okay. So if this is I call the alpha, that's called the beta, then you get alpha and the beta, f, x, y, z, and dz, okay? But the alpha or beta might depend on x, y, because when you see that, when depends on location of the point, okay? So this is the way we cut, we fill the solid using the sticks, bars, okay? One-dimensional object filling them, okay? So this is one way. Then after you evaluate this single integral inside with respect to z, then you have double integral. Then the next problem is double integral problem, okay? Another, yeah, here, alpha, beta, depends on x and y, okay? In general, okay? Sometimes if it's a cylinder, then those are constant. Yeah, cylinder is a lower bound, top bound. But if it's cone, then it's quite different. Okay? Another way to do is you project this solid onto z plane, z axis. So we have a fixed point here. That's called this is x, y. Right? So this time I have to use let's use A and B, doesn't matter, okay? So use the lowest point as the highest point of the shadow. Okay? Then this triple integral is going to be, first of all, a single integral dz, okay? But for each z, you get cross section. And that cross section is this is a depends on z, is a region, in the xy plane, okay? After you set, so this will be the double integral of this function in dA, okay? Then you evaluate that first, you get a function of z, then you evaluate the function of z, evaluate the integral of the function with respect to z. Okay, so there are a couple ways to do. Okay, so you have to deal with, and sometimes this idea works very well. All right. Next, I'm going to talk about the Crease problem, the last Crease problem. Okay. This is from which section? Triple integral. Yeah, from triple integral. Remember. Yeah. So let's consider. Now I put the z squared instead of z. Okay. But when I got home, I looked at it, found that it can be evaluated. It's not a big deal. Okay. So here the E is described by those inequalities. There are several students either corrected, but there are some still computation mistakes. So I take the point off. Okay. So first of all, you have to, it's harder to draw the graph, a region. Okay, this is a triple integral. Okay, I put the z squared there. Okay, that's the problem on the quiz. And the problem from the book is a z. The only difference is if it's a z, then you just use substitution. You get like an h logo. Okay, if it's a z squared, then you get arctangent. Okay, that's the integral. Yeah, let's do the problem. Okay, it works. Okay, so the region, how do you draw the region? It's a little bit hard to draw the region. So you have to look at that one by one. Okay, y is independent, so y between 1 and 4. Okay, and then you have to determine z value. Z is between y and 4. Then you have to determine x value. Sometimes I can switch the order here in the definition of z, e. Okay, but so here the picture is if it's harder to draw it, but this is a z, that's x, that's a y. So y is between 0 and 4. Take arbitrary y. Okay. then you find out z is going to be, z equals y is this line. Z is between y and 4. Okay, so in the YZ plane, this is a region. Okay, so if there's no restriction on x, what do you get? If there's no restriction on x, you will get something like that going this way. Okay, if there's no restriction on x. Okay, but x is going to be between 0 and z. Now, what is x when x equals z? X equals z is this line, okay? X equals z when, you know, then x is between z, so between 0 and z, x is cannot be, when z is larger than x is large. So this is going to be picture. I'm pretty sure. Okay, so this is a region. If you draw the graph, maybe you are able to even change the order of the iterative integrals. But that is a picture, roughly. Okay, so so if you feel hard to draw the graph, then what you can do is because y is already determined, so you put dy here, and you already know where the y is between 1 and 4. So now 0 and 4. Okay, somewhere here. Okay, so it does not touch the does not touch the 0. Okay, y is between 1 and 4. Okay, then you have to determine the z value. Z is between y and the 4, right? dz. Then the x is between 0 and the z. So the question is, how do you evaluate this iterative integral? So first of all, you have to recall this formula, right? This is the integral with respect to z. I think this integral will be 1 over a arctangent x over a, okay? Plus constant. You can double check it. How do you double check it? When you double check it, you differentiate. Then this goes to denominate, right? And then you differentiate inside to 1 over a. So after you simplified, a squared is cancelled out. It's just what a squared plus x squared. So that is indeed the integral. All right. So be careful. Yes. So this triple integral. So first of all, look at the z squared. Z is a constant, right? This is like a z, like a here, right? So it's going to be z squared, right? And then 1 over z arctangent and x over z, and evaluate from 0 to z, right? And then dz dy here. All right, so let's plug in. So if you plug into this, first of all, after simplifying z, because this is where some students make mistakes. Okay, so that was z there. Okay, some students forgot z squared, then just get 1 over z, cause trouble. So we plug z for x, then you have arctangent 1. You plug 0 for x, then arctangent 0. So it's not too bad, right? dz dy. But this arctangent 1 is pi over 4. Arctangent 0 is 0. So you only get z pi over 4 dz dy. Right? As long as you overcome the first, right? The antiderivative of a z squared over x squared plus z squared, then the rest of them will be simple. right? Then you find the antiderivative of z squared is half of z squared. Evaluate at the two ended points. Right? And then finally, so that will be z squared, so 2 squared minus y squared, 4 squared dy. Right? So then you find the antiderivative of that function. 16y minus 1/3 y cubed. Right? Evaluate at the two ended points. So 16 times 4 minus 1/3 4 cubed, and the minus 1. Yeah, plug 1 for x, for z. Okay, so you get the answer. Okay. The first part, let me check. The first part, 16 times 4 is 4 cubed, right? So it's 2/3 4 cubed. Okay, minus plus 1/3 plus 4 squared. So, well, you can simplify this. Okay. Okay, I'm not sure whether we can get an integer here now. Okay, so this will be 16 times 4, 64. 64 times 2 is 128. 128 plus 1, that's 129. So anyway, it's not. So this is a number. Yeah. If we have time, we can combine them into one single fraction. So I can take I think I take a 4 square out. If I take a 4 square out, 16 over 8 is 2 pi. Then here 3 over 8 plus 3 over 8, right? No, there's no way I can take it up because that's 1/3. That's it. So this will be the answer, and you can combine into one single this is a minus. Yeah, it's not. This will be the minus. Yeah, let me finish it. Yeah, I can do this computation. Okay, so I take a 4. I take a 4 square out. That'll be 3 over 8 minus 1 plus 1/3. And 4 square, it's a 5 plus. Okay, so then 4 times 5, 20, 20 times 4, 20 times 4 is 80, right? 80 plus 1 is 81. 81 divided by 3, you can do that. 81 divided by 3 is 27. Yeah, that's right. So 27 pi over 8. So that's it. Okay. There are some small mistakes I saw. Look at some students got the idea how to evaluate, but the problem here is this part. Yeah. Some forgot forgot z squared instead of, yeah, this z squared over z, then cancel, then you get a 1z left. All right. All right, now today is section 15.9, and this is about change of variables in multiple integrals. I already discussed that several times about yeah, the change of the variables. In other words, this is just substitution in for multiple integrals. Okay, so the most challenging part is how to find a substitution for multiple integrals. And you not only want to simplify the function, you also want to simplify the region. Okay, so let me review the formula. Suppose you have a very bad solid, okay, that's E in the XY plane. And then you have a much better, nice region. Could be a rectangular box. I just usually draw a rectangular box, okay? So that's E bar. And if you have a map, right? So the map is given by X, three-dimensional case, it's X, Y. Yeah, you have three variables, right? And it's Y and the Z. X is U, V, W. Y is U, V, W, depends on three variables. Z also U, V, W. Okay. Then, so this is in the U, V, W coordinate system. Then the integral, the triple integral will become for any function here, it's going to be this triple integral over the E bar. And F is still X, Y, Z, and you have to replace that by U, V, W, okay? So this part is going to be the absolute value of this Jacobian. Okay, so what is that? The Jacobian, the absolute value of the Jacobian, that is a determinant. That is going to kind of like the derivative of the map. Okay, you should understand that way. So what is this? How do you differentiate? This is defined to be the determinant of the matrix. Okay, so here partial U and then you differentiate Y with respect to U, differentiate Z with respect to U, then you differentiate X with respect to V, then differentiate Y with respect to V. Yeah, all possible partial derivatives. Okay, then it's a matrix, so you have to take the determinant. Then you get, it could positive could be negative, but you have to take up a absolute value. Now, in the two-dimension case, this is a little bit easier to understand. So you have some region, bad region here. This is called, let's call it D, okay? And this is just only X and Y. The difference here is simple. Okay, let's go backward, okay? So then here I have a little bit nice region D, and the U and the V. Let's only have it. Okay, then if you know this nice region is mapped to this very bad region, okay, and given by X equals U and V, Y equals Y, U and V, then how can I translate the double integral over D to a double integral over D bar? Well, it's a very similar formula. Okay, this will be double integral over D bar. But there is another part here called the derivative of the map. Okay, and here dA bar. Right. But this one's absolute value as this derivative of the map in the book called the Jacobian. This is the determinant of okay, so you have two variables. It's very similar, right? Now, if it's just have a one function, okay, and the interval here, that's called I. Okay, I is the interval. right, from A to B. So I'm going to use I bar, which is this is UX. So if I have a map, and this map, I just call the X, okay? X depends on U, just U, right? It sends this interval to that interval, okay? Then the integral, the single integral over I, fx dx, I just use I, don't use the AB here, okay? And this can be also written in the form I bar and f of x. Yeah, the x can be replaced by x of u, okay? Now, be careful, it's absolute value of partial derivative, not partial, dx, du, okay? And du, okay? And yeah, so be careful, when dx of du is negative, then the interval will be reversed. So yeah, this is also yeah, this is a formula in the one-dimensional case. If I want to write, if I is going to be AB, okay? So yeah, let's put AB here, and this will be A bar B bar, okay? And then this is a this is just the integral, okay? And we also use the A bar B bar here, and I have to use the absolute value, okay? If I remove the absolute value, then it depends on yeah, it depends if it's negative. If the derivative is negative, means you reverse the order of the interval. Okay. So if A bar is mapped to B, B bar mapped to A. Okay. Then yeah, in the case of it's negative, the derivative is negative, then I have to put the B bar here and the A bar on the top, then absolute value, okay? No absolute value. Then when you change when you switch the order of the interval, then you still have to remove that negative sign there. Okay, anyway, this is a general formula. Doesn't matter whether the derivative is negative or positive, okay? But here's a note. I didn't touch anything. I don't know what happened. Okay, so my note is if this is a negative, okay, then A bar becomes B, and B bar becomes A, okay, because it decreases. Okay. In that case, the formula is usually the formula. Yeah, usually we expressed in the following way, because A bar is sent to B, so this can be A bar, that's be B bar, right? And then here is a derivative, then D. But if you want to change the order of the interval from A bar to B bar, then you have to put a negative sign in front of the derivative, right? Then negative of that derivative becomes the absolute value. Okay, so that's why I just trying to. Okay, so you can put this form, yeah, in the uniform form. Doesn't matter whether the derivative is positive or negative. Right. So now we are going to work on some problems. I think it's really a bit difficult. The first one we know it's polar coordinates, right? We did that before. So if we have a map, right? So this is this is a region. Let's use this just for example, okay? So here the radius is going to be capital R, okay? Angle is theta is between alpha and beta, okay? That regions described here in the XY plane, okay? So that is my D. So actually we can find the map. Alpha, this is R, right? R is between 0 and the capital R. And this will be alpha, that is beta. That region, okay, is the center to here. Using the map, using this map, x equals R cosine theta, y equals R sine theta. Okay. Got it? Yeah, this is a center to here. So if I have to evaluate a double integral over D, I can change the variables. Okay, this is essentially just substitution. I'm going to find the derivative of the map. Okay. So the first variable is R, and the second variable is theta. This is a determinant of the matrix. When I differentiate R X with respect to R is cosine theta, and here sine theta. Okay. Then I differentiate X and Y with respect to theta, sine theta, R cosine theta. When you calculate the determinant, what do you get? You get R cosine square theta minus negative R sine square theta. It's just equal to R. Okay. Oh, maybe I'll touch the button here. Okay. All right. So according to the above formula, the double integral over this D on the right hand side is f x y dA is going to be the double integral over d bar, and here x is r cosine theta, y is r sine theta. Then this will be the absolute value of, right, and the dA bar. Okay. So this is what we got for our this is the integral in the polar coordinates, in other words, r cosine theta, r sine theta, and here's r dA bar. So because d bar is a rectangle, is a rectangular region, so you can easily simply write 0 to capital R, and here's alpha to the beta. And this will be R and d theta and dr, for example. Okay. So those are the formula we're going. So I'm going to discuss another problem from from the book. Right. So R is a region bounded by y squared equals 4 minus 4x and y squared equals 4 plus 4x and y is greater than or equal 0. So let me describe this region. Okay, x-axis, y-axis. Y equals 4 minus 4x. What is that region? What is that curve? Yeah, that curve. This is actually the parabola. Okay, this is going to be x equals a quarter of y squared, negative quarter of y squared, and plus 1. Okay, this is a parabola opens to left and start from here. Okay, when y 0, yeah, this is a when x equals 0, y is going to be plus minus 2. Okay, so here y is, yeah, this is graph. And then the other one will be, this will be x equals a quarter of y squared minus 1. So this is going to be that. And actually the region y is greater than 0. So that is the region. Okay. That is the region R. So we're going to evaluate the double integral of R and the y dA. Now without, yeah, there are a couple ways to do it. You can solve this problem directly, okay, without changing the region. Okay. So how do you do that? You can express this iterative integral. There are two different ways to do it. The first way is, this is a negative 1, this is positive 1. I'm going to look at my picture already. I use a vertical line to fill the region, right? So that means x is between negative 1 and the positive 1, dx. The only problem here is the y value. Y, for each x, I draw a vertical line. If I draw the vertical line, I can determine the y value along this vertical line. The y value is from 0, but the top one depends on the curve. Okay, so I put a question mark here. This is y dy. Okay. Yeah. Then it depends on the value of x. So I have to break this integral into two parts. Well, for x between negative 1 and 0, I know this is yeah. I know the upper bound for the y value. Upper bound for the y value, I have to use that piece of function. I think this is yeah, so it's y squared equals 4 plus 4x, right? So x is a fixed. That's why it's a square of 4 plus 4x. Okay, y dy. Then for x between 0 and 1, it's from 0 to square root of the other curve, right? Other curve is going to be y squared equals 4 minus 4x. Okay, so 4 minus 4x, y dy and dx. Then you can evaluate. Okay, and the anti-derivative y squared is just equal to half of y. So half of y squared, and then you put this into here, You get that, okay? So it's not too bad. It's going to be half of 4 minus 4x dx, okay? And then you get an antiderivative, 2 plus, yeah, let's take 2 out. 1 plus x is antiderivative is x plus half of x squared, okay? And here it's 2. It's x minus half of x squared. Okay, so now you evaluate. You put a negative sign inside. It's going to be -1. I put a negative here. Plus 1/2. And this will be 1 minus 1. Okay. So just double it, right? So here's 1/2 times 2. 1, so answer is just 2, okay? So this is one way you can evaluate the integral. Another way you can do is, I don't know which one is better, okay? So you have 2 curves, right? Here's y squared equals 4 minus 4x. That one is y squared equals 4 plus 4x. So this time I'm going to use horizontal lines to fill the region. Then you will see that that means you have family of a horizontal line depends on y variable. The first no restriction on y variable, it's between -1 and the +1, right? So this double integral can be changed to the iterative integral, and the y is between -1 to +1 dy. And the x, you have to solve for x. Okay, for given y, you have to solve for x. The one on the left-hand side, okay, is going to be determined by this piece, right? So x is going to be 4 minus y squared divided by 4. Okay, this will be y squared minus 4 divided by 4, and here's y and dx. Okay. All right. So what is the next step? Evaluate, and y is a constant. Take the y out, and take a difference of the 2. If you take a difference of this 2, y squared minus 4 minus y squared, I get 2y squared minus 8. Then I divide by 4, right? So I get, yeah. If I take a 1/2 out, yeah, 2 divided, yeah. All right, so now the antiderivative is a little bit complicated. I'm not sure this is going to be 0 now. Something's wrong with here. Let me double check. Huh? Looks like, okay, double check, okay. So y value is from, oh, y is from 0 to 1. That's why my mistake. We already assumed that y is a part, okay, only the top part, okay, because I was worried about getting 0, okay, yeah. So y is between that, right? Then antiderivative, here's y cubed minus 4y, so a quarter of y cubed, y to the 4th power, minus 2y squared. Okay. Yeah, let me double check. Whew. Did I get different answers? Okay. So it'll be quarter minus 2. Okay. So y value is going to be when x equals 0, y is, no, let me double check. When x, oh no, it's 2. It's not, I forgot this. It's a negative. From from negative to the positive 2. Double check. When x equals 0, y is between, yeah, y is between 0 and 2. Okay, so that's 2. All right, so otherwise there'll be a problem here. Then everything's correct. Okay, so it's going to be 1/2. The first part, I still have to check. There's some science mistakes here. And let me double check this part. Which one is on the top? Okay, which one is on the right side? Okay, let me go back to the equation. So 4. You see, that was a mistake here. So this for this curve on the right, and here's negative. Okay, so that means I have to switch the order of yeah. So the screen too small. Sometimes I cannot go back to look at. Okay, so this will be small change here, and here the top one is 4 minus y squared from here. This one will be y squared minus 4. This should be smaller. Okay, so when I take the difference, my difference here is 4 minus y squared instead of. Okay. So will be negative, this will be positive. Otherwise, I get a negative value. So when you see a negative value, something's wrong with that. All right, you have to change it. So this will be 4, negative 4, and here's 8. That sounds so good. Okay, so many small mistakes. Okay. Anyway, I recognize that this is first of all, I see that, okay, it's going to be 0. That's impossible. Then I say, oh, because the original requirement is the y is greater than or equal to 0. So y starts from 0 to 2. Then also I copied the wrong function. This is a 4 plus 4x, right? And my top one is a 4 plus 4x on the right-hand side. Yeah, I put 4 minus 4x. All right, so anyway, you get the same answer. Now, what we're going to do today here is I'm going to change this bed region. Okay, I use, let me copy this. Right, so I'm not going to draw the whole graph here. So this is y squared equals 4 minus 4x, 4 plus 4x, yeah. Y squared is a 4 minus 4x, yeah. All right, so the map we're going to use is x equals u squared minus v squared. Y equals 2ue. Okay, so we have to determine the region. Yeah, let's compute the Jacobian of this. Okay. So this is going to be the determinant of the derivative will be derivative x with respect to u is 2u, derivative y with respect to u is 2v. Then you differentiate with respect to v, then you get 2u. Okay. Then what we get here is going to be 4u squared minus negative 4v squared is 4v squared. Okay. So it's positive. Right? It is positive. My the next part is to determine. You have to determine the domain UV for that part. Okay. So this is a difficult part. So this is my D, right? Okay, how do we check that? Look at the equation. X, say, y is always greater than or equal to 0, okay? But look at the x, the x value, okay? We know that x is between y squared minus 4 divided by 4 and greater than y squared. Yeah, there's actually 4 squared minus y squared. Four minus y squared over 4. Okay. So our transformation here. Okay, our transformation here. This is u squared minus v squared. Is less than 2uv minus 4 over 4. Okay, and greater than or equal to 4 minus 2uv over 4. Okay. Yeah, let's look at the equality part. Equality part. When you look at this equality part, you get 4uv squared minus 4v squared equals 2uv minus 4. Okay. Yeah, I'm trying to figure out the region, the pre-image. This is a y squared. So you get x squared minus v squared equals u squared v squared minus 1. Now, this does not give you a clear picture of the region. Actually, this is going to be mapped from 0 to 1, and yeah, this region from 0 to 1 and from 0 to 1, right? Yeah, when u changes from, yeah, when look at this, when uv are positive, the y is greater than 0, okay? So I just needed to see this side where it goes and this side, the 3 sides, okay? And find the relationship. It's, yeah, let me erase this part. So when this line, okay, when the v is 0, okay, when v is 0, let's see, when the v, when u, first of all, look at when u is 0, this is on the v-axis. When u is 0, x is going to be negative v squared, right? And the y is going to be 0, okay? So v changes from 0 to 1, then we will get this part, okay? Okay. Then when u equals 1, then x is going to be 1 minus v squared, and y equals 2v. Okay. So you will see that when it's y squared is going to be, then you can see that y squared is going to be 4v squared, right? For the how to get 4v squared, this is going to be 4 minus, this is going to be 4 minus 4x. Okay, so 4 minus 4x y is a y is a 2 y is 2v. Yeah, 2v, so it's y is 2v squared. Okay, and this is going to be 4 minus 4x because x is a 1 minus v squared. Okay, x is 1 minus v squared. Okay, so so this piece, when u equals 1, this piece, right, is going to be that piece. So I'm going to use a different colors to show you. So this is a piece going to here. Okay. So when u is 0, this is a piece. The yellow part. Okay. Then it's clear that this piece should be going to be here, and that piece is going to here. So it's deformed, a little bit deformed. It's hard to see that. It's this deformed. This whole region, this whole region is mapped to that irregular plane. Okay. So once you understand, this is a given actually in some problems. So now we're going to translate the double integral of that d is y, right? And the dA is going to be over that square. So y is going to be 2uv, okay? And the determinant is going to be 4u squared plus 4v squared, and then dA. Okay. And then this is just the iterated integral from 0 to 1. From 0 to 1, doesn't matter which one you want to use first. I put 8 on the outside. So I will get u cubed v, and here's the v, u cubed v and the u v cubed, and then this will be inside du and dv. Okay. So let's evaluate this integral, and that is going to be antiderivative of this with respect to u is a quarter of u to the 4th power and half of u squared v cubed. Okay. And then you plug 1 for u, I get a quarter of v plus 1/2 of v cubed. Okay. And this is a dv. This integral from 0 to 1. Then you have to find antiderivative of the function inside. So you get quarter here, 1/2 of v squared, and then 1/2 quarter v to the 4th power. And then finally get 1/8 plus 1/8. So the answer is 2. So this is the same answer. All right. So let me look at another problem, problem from the book. That's problem number. I just want to set up the integral. Okay, so this is a triple integral, a double integral. Yeah, x plus y and e to the x squared minus y squared and the dA. So R is the rectangle region enclosed by the lines. Has those two lines, x minus y equals 0. And another one is x y minus y equals 2. Then x plus y equals 0. X plus y equals 4. Equals 3. Now, how do we understand this this region? You have x minus y equals 0, so y equals x. So this is the line. Then x minus y equals 2. So that means there's another line here, y equals x minus 2. Okay? So this x minus y equals 2. This is x minus y equals 0. Then x plus y equals 0 is this line. Then x plus, the other one is this. Okay? It could be a parallelogram. Okay? So how can I find the good map which sends a nice rectangle to here, right? This is not in the right position. So what I'm going to do is I use x minus y equals u. How about like that? And x plus y equals 3. Okay? So x minus y is between 0 and 2. So u is between 0 and 2. That's easy, right? And x plus y is between 0 and 3. 0 and 3. So this one will be sent to there. So all I need to do is just solve for x. Okay? Add them together. X is going to be u plus v divided by 2. Then I take the difference. Y is going to be the second equation minus the first equation will be v minus u divided by 2. Okay? So this is a map. You can just like solve the inverse of them. Okay? And that's perfect. Yeah. So it will send this rectangle region onto this rectangle region, maybe sometimes a parallelogram. Okay? And in that position. Yeah. Okay, so if you draw, if you fix the U, okay, so let's look at the picture here. If you fix the U, then you get a bunch of lines like this where it's go. Okay, so those lines, V changes, but use V change. Yeah, for each line, U is fixed. U is fixed, where x minus y equals U. Is going to be this line. Okay, so I've got a bunch of lines like that. Okay, so this is a x minus y equals u for the fixed u. Okay, for the fixed u, you get a vertical line. Then the corresponding, the image will be those lines. Okay. Anyway, so let's set up the integral, right? And I have to compute the Jacobian. It's not too bad, right? So it's determinant of the derivative of x with respect to u is 1/2. Derivative of y with respect to u negative 1/2. The derivative of x with respect to v is 1/2. Then this is a positive 1/2. So it's going to be quarter minus negative quarter is 1/2. It's constant math. Okay. All right. So all we have to do is just x plus y, right? So this integral, the double integral, and the region is R. X plus y e to the x squared minus y squared dA, right? Yeah, x squared minus yeah. So so this will be the integral over R bar, right? x plus y, I know that x plus y is simple, just a v. And e to the x minus y, that would be x squared minus y squared equal x minus y, x plus y, right? So x minus y is u. X plus y is just a v. Great. And then you have the dA change it to the half of dA bar, right? Because the Jacobian, right? That's it. So v is between 0 and 3, and u is between 0 and 2. Okay? And then you evaluate this integral. Okay? So v is between 0 and 3. Let's go back to the picture. Yes. Right? V is between 0 and 3. So then you evaluate this integral with respect to u here. So with respect to u, the antiderivative is just e to the uv. Because when you differentiate with respect to u, you get v times e to it. Okay. So then you replace u, substitute 2 for u is 2v, then substitute 0 for v, it's 1. Right. Then you find the antiderivative of this. Then you plug 3 for half of e to the 6 minus 3 minus 1/2 minus 0. So that is the answer. Okay. All right, so that's it. Well, it's most of the time you are given the transformation, but the last problem you're not given the transformation map. Okay, you have to find out by yourself. But in some cases, it's easy to find out. In some cases, it's not easy to find. Right. For this one, the region is rectangle. Okay, and I think that we can easily find out the transformation here. Okay, so you have to do some exercise when you get home. I'm going to give a review on this part also. So we're going to have another test so next Wednesday. Okay. Oh, after break.